You know, almost everything you do online, sending an email, buying something, just browsing, it's all protected by something that feels, well, like a magic trick. It's like whispering a secret across a super crowded, noisy room and knowing only one person will hear it. Pretty cool, right? Well, today we're going to pull back the curtain and see exactly how that trick is done.
So, let's think about this for a second. How do you share a secret with someone you've never met? You don't have a secret handshake, you don't have a prearranged code. How do you lock a message so that only they can open it, especially when you know other people are listening in? That's the huge puzzle that the RSA Cryptosystem was designed to solve. Okay, so let's get into Section 1, the Secure Lockbox Problem. This is all about sending a private message right out in the open. You know, this is the classic key distribution problem. Think about it. If I put a message in a lockbox and mail it to you, I still have to send you the key, right? Well, what stops an eavesdropper from just grabbing the key in transit, making a copy, and then reading our message? It feels kind of impossible, doesn't it?
All right, on to Section 2, a tale of two keys. This is where we get the big breakthrough of asymmetric encryption. So back in 1977, three guys, Rivas, Shamir, and Adelman, they came up with this absolutely revolutionary idea. They asked, what if the solution isn't one key? What if it's two? Two completely different keys that work together as a pair.
And that's the core of what we call asymmetric encryption. It's a system that uses a matched pair of keys. You have a public key that's used for locking the message, and then a totally different private key for unlocking it. And here's the most important part, the absolute game changer. The key that locks the message cannot be the one that opens it. They're a one-way street.
So you can see how this totally solves that old lockbox problem, right? Here's how it works. You keep your private key completely, totally secret. Nobody ever sees it but you. But your public key? You can shout it from the rooftops. You can give it to everyone. And now anyone in the world can use your public key to lock a message and send it to you. But, and this is the magic, only your secret private key can unlock it.
Okay, Section 3, the clockwork math trick. So how in the world does this actually work? How do the lock and key do their thing? Well, it all comes down to a special kind of math called modular arithmetic. And don't worry, it's easier than it sounds. Just think of a clock. When you go past 12, what happens? You don't go to 13, you wrap right back around to 1. That clockwork math is the secret ingredient that creates this perfect, reversible loop.
And the process itself is actually pretty straightforward. Here's the whole journey in 5 steps. First, we take your message and turn it into a number. Then, we use the public key to lock it, or scramble it, really. That gives us our scrambled message, which we call ciphertext. Then, on the other end, the private key is used to unlock it. And just like that, poof, the original message is back, perfectly clear.
And here's a super simplified example with some actual numbers so you can see it in action. Let's say our message is the number 123. We run it through the encryption calculation with the public key, and it turns into this random-looking number, 855. But then, when the recipient applies their private key, that clockwork math does its thing, reverses the process, and boom, we get our original 123 back. It's amazing.
But wait a minute, what's the real secret here? I mean, how do these numbers just magically reverse each other? How can these two keys be so perfectly linked that one undoes the other, but the public key gives away absolutely zero clues about the private key? That's the million-dollar question.
And that brings us to Section 4, the secret of primes. This is the elegant mathematics behind all the magic. And you know what? The secret isn't some ridiculously complex formula. It's actually hidden in the simple, beautiful properties of prime numbers.
You see, the entire security of this system, the thing that makes it so hard to crack, relies on a really simple mathematical asymmetry. It's based on a math problem that is super easy to do in one direction, but incredibly, unbelievably difficult to do in reverse. Here it is. It's easy for a computer to take two massive prime numbers and multiply them together. That's simple. But it is insanely hard to take that gigantic result and work backwards to figure out what the two original prime numbers were. That's called the integer factorization problem, and that is the shield that protects RSA.
So when we talk about how strong this is today, you'll often hear this number 2048. And what does that mean? 2048 bits of security? That means the final number you get after multiplying our two secret primes together is a number with more than 600 digits. I mean, just try to imagine that.
And it all comes back to that beautiful, elegant difficulty of factoring two massive secret prime numbers. All that security boils down to one simple fact. Multiplying them is easy, but factoring that 600-digit result back into its original primes? Yeah, that would take even our most powerful supercomputers billions of years. That's security. And here's a really fascinating piece of history for you. We all know RSA from Rivest, Shamir, and Adelman in 1977. But it turns out the algorithm was secretly invented 4 years earlier, in 1973, by a guy named Clifford Cox at GCHQ. That's the UK's version of the NSA. His incredible work was classified and kept secret from the public until 1997. Crazy, right?
Just to prove how tough this factorization thing was, back in 1978, the inventors put out a challenge. They offered $100 to anyone who could factor a 129-digit number they created. And you know how long it took? 16 years. It wasn't until 1994, with the help of thousands of computers working together over the internet, that it was finally cracked.
Okay, let's move on to Section 5, RSA in your daily life. Because this is where we answer the big question. Why does this all matter to you? Well, because this incredible mathematical magic trick is running silently in the background of your digital life every single day.
I mean, look at all this. You ever see that little padlock icon in your web browser or the S in HTTPS? Yep, that's often RSA at work. It's used for digital signatures to make sure documents haven't been tampered with. It's inside the VPNs we use, our secure shell connections, and even in secure email like PGP. It is, quite literally, one of the foundations of our digital trust. Now, RSA isn't perfect. It has one little weakness. It's kinda slow. I mean, all that heavy-duty math takes time. So, what we often do is use a clever hybrid system. We use the slow, super strong RSA to encrypt just one tiny thing, the key for a much faster system like AES. It's like using a big, clunky bank vault key to safely pass a tiny, fast race car key. You get the best of both worlds, unbeatable security to start the conversation, and then lightning speed for the rest of it.
So, for decades, this lock, this brilliant mathematical lock, has been considered practically unbreakable by any normal computer we can build. But there's something new on the horizon. A totally new kind of computer is being forged, one that doesn't play by the same rules at all.
And that threat has a name: Shor's algorithm. It's a theoretical algorithm designed to run on a quantum computer. And here's the scary part. It could solve that impossibly hard factorization problem, not in billions of years, but maybe in a matter of hours. Now, these powerful quantum computers don't fully exist yet, but believe me, the race is on to build them. And that brings us to the final, provocative thought. The lock is brilliant, but quantum computers are learning how to pick it. This whole thing is a constant cat and mouse game. RSA was an absolutely brilliant lock for its time, a true revolution. But as quantum computers get closer to reality, the world's cryptographers are already hard at work designing the next unbreakable secret. Which leaves us with one question: what will the next great magic trick look like?